This example is about doing a staged construction of an embankment on soft ground, and the objective primarily is to monitor the pore pressures and the stability during construction, and in the end we will demonstrate that it is possible to determine the rate of loading to maintain stability during construction. We're going to start going through the detailed steps of doing this analysis with the fast loading, and the fast loading will be where we place 1, 2, 3, 4, 5 meters of fill. Each meter of fill is placed supposedly during 1 day. We want to watch the increase in pore pressures during that time, and then in the end, when we have the peak pore water pressure, excess pore water pressure, we want to do a stability analysis. So here's a summary of the exercise. Place the fill 1 meter a day. In other words, in our time stepping, it's the duration is 1 day. We need to construct an analysis tree, and we need to apply the appropriate boundary conditions for each of the analyses in the tree. We need to start by establishing the in situ state of stress in the ground, noting that the initial water table is 1 meter below the ground surface, and the material properties have been provided for you in order to save some time during this demonstration. The fill material will be treated as a total stress material because we don't want to deal with the pore water pressure in the fill. We could assume, for example, that the fill material is very granular and the pore pressures are not of consequence in the fill, and one way of doing that is to use the total stress properties for the fill. And what we then want to do is look at where we have the maximum pore water pressure conditions, excess pore water pressures, and to check the stability. And as it turns out, it will be when we place immediately after we place the last lift on day 5. And as we will see, that this fast loading will lead to a factor of safety that is close to 1, suggesting that this rate of fill placement is too fast to maintain stability. In GeoStudio, the file is SIG 12, and when you bring up the file and you are in the GeoStudio desktop, this is what you should see. We have set up the geometry in order to save time as part of this exercise here, and the initial analysis, which is an in situ analysis, has already been created with the appropriate boundary conditions. Key end analyses, notice that we have here an in situ type of analysis, and we are going to get our initial pore water pressure conditions from a definition of a water table. Key in material properties. We have a material here that we have created specifically for establishing the in situ stress state. Notice that we have selected effective drained because we have a water table, and in order to get the correct total stresses, we need to deal with the pore water pressures, effective drain parameters, a linear elastic constitutive relationship, which is not all that important. The Young's modulus is not all that important. However, The unit weight of the soil once again has been selected as 20 kilonewtons per meter cubed for the in situ analysis, with a Poisson's ratio of 0.36. This represents a K0 of approximately 0.56. As we will see here in a moment, the soft clay is going to be represented with a modified CAM clay type of constitutive relationship, and the friction angle that we are going to use is phi is equal to 25.6. This value for a effective friction angle means that on a P prime plot that the slope of the critical state line is at a 1-on-1, and this makes it easy to spot check the results. Now, having done that, there is an expression for soft soils that says that the K0 is approximately equal to 1 minus sine phi, and if we take 1 minus sine 25.6, it comes out to 1 minus 0.444 approximately, which makes K0 approximately 0.56, which makes Poisson's ratio the equivalent 0.36. So this is how the Poisson's ratio was selected in order to get a K0 value of approximately 0.56. So that is the material that was created purely for the in situ analysis, and we should now be ready to compute the in situ stress state. Clicking on Solve. Very quickly spot checking the results. We are plotting here the pore pressure starting at 0. We notice that it corresponds to the specified position of the water table. We could also add a contour of Y total stress. And since they're perfectly horizontal, it appears that the stresses have been computed correctly. So having then established our in situ stress state, we can now proceed to apply the first lift. Going back to the define view then, under key in analyses, we need to clone this analysis, calling it first lift. The type of analysis is now a coupled stress pore water pressure type of analysis, and the first lift has a parent which is the in situ. We are now going to get our initial stresses from the parent, and we are also going to get our initial pore water pressures from the parent analysis. We said that we were going to place this first lift in 1 day, so the duration is 1 day and the number of steps is 1, and so we have a 1 day delta t, an increment of 1 day. assigning the appropriate materials for this loading phase. Draw materials. Our soft clay, looking at the properties, notice that we are now selecting the category as effective parameters with pore water pressure change. We have selected a constitutive relationship for modified cam clay, and over consolidation ratio of 1.2. Here is the same Poisson's ratio as we use for the in situ. The slope of the normal or virgin compression line is 0.2. The slope of the rebound curve is 0.04. The initial void ratio is 1.5, and we will not be applying the self-weight of the soft soil. That took place in the in situ analysis, and here is our effective friction angle, 25.6 degrees. And notice that the slope of the critical state line is 1. As noted in the one-dimensional case, we always must specify a volumetric water content function, and so here we have used a volumetric water content function. I won't dwell on this except to note that we need a volumetric water content function. We need a hydraulic conductivity function. And those are all the properties for the soft clay. So we can assign the soft clay to this region here. We have another material which is the superficial desiccated crust, which is the upper meter as a superficial desiccated crust. In this particular case, we have said that it will be effective parameters with pore water pressure change, like in a coupled analysis. However, considering that the soil is desiccated and likely stiffer and not as soft, we have, in this case, for illustrative reasons, just used a linear elastic constitutive relationship with a constant Young's modulus of 2000 kPa. Also, the unit weight has not been specified because we do not want to apply the self-weight in this particular analysis for the desiccated crust. And once again, we have used the same Poisson's ratio as for the subsurface softer clay. It's not all that important here, but we have used the identical volumetric water content function and the identical hydraulic conductivity function that we used for the soft clay. So we have now created our soft clay at depth and the desiccated crust, and we now want to place the sand fill in the first layer. And as we noted earlier, we are going to use total stress parameters for the fill. In this way, we do not need to talk about the pore water pressure in the fill itself. Once again, a linear elastic constitutive relationship, constant Young's modulus of 2000 kPa with a total unit weight of 20 kilonewtons per meter cubed. We need to do one other thing, and that's to apply our boundary conditions. Draw boundary conditions. We have a fixed in the x direction. We need to fix this boundary here representing the first lift. Fix the displacement in the x direction. Now when the fill gets placed, the water table was here, And as the fill gets placed and water gets squeezed up into this layer, the water table is going to come up. And the assumption is that the fill is quite granular, and any water that squeezes out of the soft clay and arrives in the fill will disappear by seepage through the fill. And then, so we don't want the pore water pressure to become any higher than 0 on the ground surface, and therefore we need to apply a surface hydraulic boundary condition that is a potential seepage face. Draw boundary conditions, key in the ground surface. Notice that we have selected potential seepage face. And in a potential seepage face, we say the total flux is 0, the action is 0, and so sigma W will, if the pore water pressure becomes greater than 0, then the boundary condition will be created, switched to a total head equal to the elevation. Draw on the line a potential seepage face. So we have assigned our materials, defined the material properties, set the boundary conditions for the stress-strain behavior, and set the hydraulic boundary conditions for the seepage part of the equation. We should now be ready to analyze this situation once the first lift has been placed. Very briefly, we need to look at the results to make sure that we are at least tending in the right direction. We have a deformed mesh here. Draw vectors. The magnification is only 1. At this stage, let's make the magnification 10, and we see that we seem to be tending in the right direction with the displacement. Let's turn off our deformed mesh, and let us contour excess pore water pressure. And as we see, here are our excess pore pressures. These are pore pressures that have been generated as a result of the placement of the first meter of fill. And that seems to be reasonable, that the largest excess pore pressures are under the center line of the embankment, and we seem to be tending in the correct direction. So let's assume that we have done everything correct at this stage. Going back to the defined view, we can now begin to place our fill in layers under key in analysis. We clone the first lift and say second lift. And the parent now becomes the first lift. Once again, we want to place the lift in 1 day, so our delta T is 1 day. Draw materials, adding the fill material to the second lift, and finally draw boundary conditions. That's not correct. We need to remove that boundary condition, and we need to assign the x displacement equal to 0 on the left edge. Now once again, we can either create 3 more analyses and then assign the material and properties and boundary conditions rather, or we can do it 1 lift at a time. I'm going to now create 3 more analyses to represent lift 3, 4, and 5. Clone, and this is the third lift. And the parent now becomes the second lift. clone again. This becomes the fourth lift, and the parent becomes the third lift, and finally cloning it again, we have the fifth lift, and the parent becomes the fourth lift. Now, once again, to repeat, in each one of these cases we have a duration of 1 day. So what we are simulating is placing the fill in 1 day, and whatever consolidation and dissipation takes place during 1 day is acceptable, but a lot of the excess pore pressure will obviously not dissipate. Going back then to the second lift, we need to now, the third lift, draw materials, placing our fill. The third lift is the third layer, has the cross hatching, so that is correct. Draw boundary conditions. Displacement x is 0. Fourth lift, draw materials, sand material fill, and now the cross hatching should be in the fourth lift, and our boundary conditions, draw boundary conditions, displacement x is 0, and finally going to the fifth lift, draw materials, sand fill, and the cross hatching now should be in the fifth lift, which it is, saying draw boundary condition fixed x, for interest's sake, let us add one more analysis, and let's call it the dissipation analysis. Clone the fifth lift, call this the dissipation analysis, and our parent is the fifth lift, and let us model and look at what the dissipation of the pore pressure looks like over 30 days. So we now have a duration of 30 days, and let us say that we have 10 time steps during that initial 30 days, and notice that the total elapsed time now is 35 days. We don't need to change any boundary conditions, no material properties, but notice that during the dissipation analysis now, we don't have any cross-hatching, showing that we are not applying any further load. We're just dissipating the pore pressure after the last lift was placed. Clicking on the Save icon, we should save the problem. Clicking on the Solve icon, then, we can proceed to select all of the analyses and click on the Start button and go analyze the whole process from in situ analysis to the dissipation phase. And it takes a few minutes to make all the calculations. But notice that we are now doing step number 1, and already there were some boundary reviews. The boundary conditions were adjusted as the zero pore water pressure contour intersected the original ground surface. So at each time step, then the boundary is set back to the initial definition, and then the review process takes place through each one of the different analyses and time steps. So this takes a few minutes to do. We are now in the fourth time step, applying the fourth lift, now the fifth lift. And finally, step number 6, we are now in the dissipation phase of the dissipating the excess pore pressures. Going to the results view then, let's say draw a graph, and we'll look at the pore water pressure beneath the center of the embankment. The location that we are looking at is right here. We're looking at the pore pressure at a node at that particular location underneath the embankment. Show the graph, and we see here that we have the pore water pressure increasing as we place each lift. 1, 2, 3, 4, 5, and the peak pore water pressure at that particular point in the domain after we've placed our last lift to complete the embankment, and then we see the pore water pressure dissipating with time as the consolidation takes place. We can look at the settlement, and we are looking at the settlement underneath the embankment and some distance outside the toe of the embankment. And when we place our first lift, once again we see that the maximum settlement is sort of under the crest of the lift that was just placed. Holding down the control key, we can see the second lift, third lift, fourth lift, and the fifth lift. The point here is that we are getting very little consolidation, but we are still getting some compression of the soft clay and some settlement of the soft clay. Now, from the peak settlement, the settlement when the last lift was placed, up to the end of the dissipation at a total elapsed time of 35 days, we can see how much the ground has consolidated and settled along the original ground profile. We can also look at the pore water pressure profile throughout the soft clay and the original ground. If we are looking at the pore water pressure profile inside the original subsurface, notice that we use total stress parameters in the fill, and therefore we have no pore water pressure information in the fill. And initially, of course, it was hydrostatic with depth, and then we placed the first lift, and we had a 100% pore pressure response, but a little bit of response at the surface in the negative zone as well. And then the pore water increases as we continue to place more fill, but the pore pressure never exceeds a 0 at the original ground surface because of our seepage face review on the ground surface. If we then plot the fifth lift and look at the dissipation at the end of 35 days, we see that we still have substantial pore water pressure in the subsurface after 35 days. We could alter this graph to look at excess pore water pressure, and we see that there is still substantial excess pore water pressure at the end of 35 days. Well, there are just a variety of ways that we could look at the results here, and you can look at them whatever interests you, but at this stage we want to just illustrate the procedure and the techniques for doing a coupled analysis. And now we want to look at the margin of safety of the embankment when we had our peak pore water pressure conditions. Going back then to the defined view, under key-in analyses, let us add a slope analysis where we are using sigma W stresses in the stability calculations. We are using a slope W analysis using sigma W stresses. Slope W, sigma W stresses. And what we want to do, let's call this simply stability. And our parent is the fifth lift when we had the highest pore water pressure conditions. We're going to get our stresses from the parent, which was the fifth lift. We're going to get the pore water pressures from the fifth lift, and we are going to get the pore water pressures from day 5 and the fifth lift. Day 5 on the fifth lift. It's important that we select the proper time to get the peak pore water pressure conditions for the stability analysis. Slip surface, let us select enter exit to define our trial slip surfaces. Key in materials for the stability analysis. The properties have already been defined for you. All we need to do is say draw materials for the desiccated crust, the soft subsurface clay, and the sand fill. We need to define the extents of our trial slip surfaces, draw slip surfaces, enter exit, defining a range of enter points for the trial slip surfaces and a range for the exit of the trial slip surfaces. And this is personal preference, but I like to always round off these numbers. In my view, it makes my interpretation less complicated. And let us say that we want 5 increments here and 5 increments on the exit and 10 radii. Apply this, and so there are the definition of our trial slip surfaces. Clicking on verify and then clicking on solve, we can solve for the factor of safety. We have a stability. Somehow I got an extra slope analysis in here. Let's delete that slope analysis. That was not the intent. We wanted the stability at the end of 5 days when the last lift was placed. Clicking on Solve, we can solve now for the factor of safety. Looking at the results view, we have turned on our safety map, indicating that there is a fairly wide zone where the factors of safety are all quite similar. And this would suggest that we have a situation where the embankment has been placed too fast. At this level and at these pore water pressures, the factor of safety is very close to 1, indicating that we would likely get failure, and so we need to likely place the fill at a slower rate such that we get a higher factor of safety during construction. Now you can say draw a graph and look at things like pore water pressure distribution, and we notice that we get a peak pore water pressure of about 95 kPa along the slip surface. And once again, here's our driving force and our resisting force, and the ratio of the two gives the local factor of safety, which we talked about in Sigma session 1. Let us go back to the define view and select the fifth lift to look at, and go to the results view, and let us plot the pore water pressure starting at a pore water pressure of 0, incrementing by 20 and 10 and 10 contours. If we go back now and look at the in situ case, of course, the 0 pressure is at the position of the original groundwater table. Looking after we place the first lift, notice how the 0 pressure line has risen. In other words, water has been squeezed up into the original desiccated layer. And by the time we hit the second lift, we see that the 0 pressure line now has met the base of the fill almost over the whole distance. And by the time we go to the third lift, then it's outside of the toe of the embankment, we already have 0 pore water pressure. It is just interesting how we started with a negative pore water pressure in the desiccated clay, but in essence what we had here was a unsaturated, saturated ground condition, but sigma W can handle this case, and we can see as water gets squeezed out of the soft soil that the water goes into what was originally unsaturated and then goes to 0 because of the specified boundary condition. One other thing that I should draw your attention to that can be rather interesting sometimes is you can say draw vectors, and we can actually show the flow vectors in a case like this. And the reason we don't do this very often is, of course, draw vectors. Let's make the vectors a dark blue, and we'll make the magnification 1. And so now you can see the direction of the flow at this particular instant in time. Vectors can be very confusing. Draw vectors, and the reason here is our magnification is way too big, making the magnification smaller, maybe a little bit bigger, maybe 100. And we can now see with these arrows the two-dimensional flow due to the dissipation of the excess pore water pressures. Once again, there are a variety of ways of looking at the results, but for this illustrative workshop example, this is likely adequate to illustrate what can be done. Going back to our PowerPoint presentation, we have now checked the stability by placing the fill very rapidly, 1 meter a day, and this analysis indicate that the fast loading would likely result in instability because the factor of safety is too close to unity. Now, as a class exercise, I would suggest to you that you save this problem under a name using File Save As, save the problem under a different name, and then repeat the analysis, but make the duration for each one of the fill, say 6 days, and then reanalyze the problem and take another look at the factor of safety. Doing a file save as in this particular case is better than repeating all of the analysis in the same file. In this case, it's faster and more convenient. So once again, as an exercise, you can alter the duration for placing each of the lift to 6 days, having then 6 time steps for each analysis, and then repeating the calculations, everything else being the same. And if you do that, then you will notice that the pore water pressure increased when we placed the first lift, but then there was some dissipation. Then it increased in the second lift, some dissipation. Increased second, third, and dissipation, fourth, and dissipation, fifth, and then the dissipation phase itself. Now, and if you recall, then when the duration for each lift was 1 day, we had at this particular point excess pore pressure somewhere as close to about 95 kPa. Now it is around 75 kPa. So all of this dissipation or consolidation that took place while the lift was sitting in between the fill placement has resulted in a lower overall pore water pressure condition, and as a result we get a higher factor of safety. So if you are going to repeat this exercise, recall that we had a factor of safety very close to 1 with the fast loading. Now when we are doing slower loading with lower pore water pressure, we get a factor of safety that is higher and maybe even acceptable during To those of you who are more interested in this type of an analysis, we have done some case history studies. There were some test embankments constructed in France. It's getting now to be a long time ago at a location in western France, Coupsac-le-Pont, and there were some test embankments. One test embankment was built so fast that to determine at what point the embankment would fail, and upon reanalysis and following the same procedure, you see here we get a factor of safety close to 1 when the embankment did indeed fail. Then a second embankment, a lower embankment, was constructed, and it was left there for a period of 5 years with a tremendous amount of instrumentation to monitor pore pressures and settlements over a long period of time. So to those of you who are interested in this type of an analysis, I refer you to these case histories in our detailed examples that we ship with the product. This then brings us to the end of this coupled analysis, where we have done stage construction with a coupled analysis, watching the excess pore pressures with fast loading and slow loading, and then showing how this can be used in a slope W stability analysis to check the margins of safety and stability during construction.